All right, is this working? Yes, awesome. Yeah, so it's been a good 2 weeks or so for us actually, because have any of you read about the Google SyntaxNet parsey-mech parseface thing that has been released? Yeah, so fortunately for us, the world has decided that syntactic dependency parsers are now artificial intelligence. So woohoo, people like, you know, there's now awesome hype behind these things. But in practice, these are actually relatively low-level tools. But I've been developing these things for quite a while, and I'm excited to tell you about the library. So another way to kind of think about this, if you've been doing other data science outside of Python, is that it's just like Stanford's core NLP, which has been developed for about 20 years now, and is one of the other really production-ready natural language processing solutions. But there wasn't really anything like this for Python. Natural language toolkit, it has some different concerns and is mostly geared towards education and kind of dipping your toes in. Whereas I really wanted something that kind of helped you really build things. So I'll just switch over to like this code example just so that you can kind of see the goods up front, so you can get an idea of what this thing does and how it looks and everything. So one of the things that we really tried to do, unlike a lot of data science toolkits and data science libraries, was really get the ease of installation down. So pip install spaCy and conda install spaCy should always just work, and then there's a simple command to download the data. And then from there, we really have tried to keep the API quite clean and really tamp down on the configuration and stuff, and really get people productive to start with. So, you load the models and then immediately you're able to just process text through it. You can export the analysis that you do on the text to NumPy arrays, and there's also a global interpreter lock-free multi-threading because the underlying library is written in Cython. So we get to use this, essentially write it in C-ish sort of code and release the global interpreter lock around the main bit of the pipeline. So I'll explain all of this as we go. All right, so that's the kind of like very quickest thing. I'll just zoom through some other things. We're starting to see some good traction from users, and a few people are using us in production now. And also the performance is better than any other libraries that are available. So in particular, the speed measured in words per second is better than any other natural language processing solutions available. All right, so before I started, developing this and entered the kind of startup world, I was an academic. So mostly I've been used to doing academic talks. So I was thinking a little bit about how to do, a talk like this for a programming audience. What I've understood from prior art is that the way you do this is you give tortured analogies with lots of pictures and things. So after thinking a while, I decided that, all right, it's time to do this. So basically what I'm trying to get across here is that the library that I'm talking about, spaCy, is quite a low-level tool. It's not actually a cake. It's a thing that helps you bake the cakes, where the cakes are language technology applications. So, and then if we're talking about this, well, what sort of cake baking apparatus is it? Well, it's kind of like an industrial kitchen. So, the idea is that we want you to be able to do, basically good work and put this in serious products and make lots of money. So, it's designed for this kind of repeat use and high efficiency and this sort of thing. On the other hand, it's, design's all about trade-offs. And for some users, if this is, basically your first dabblings in natural language processing, the learning curve is still a little bit difficult in some ways. And, also, as I say, it's not exactly safety first or second, or even maybe sixth. So, we're not actively trying to push you into the industrial cake mixer or something, but if we can remove a guardrail and make everybody more efficient, then that's a thing that we consider doing. So, in contrast, maybe some of these other tools are, basically give you a different sort of vibe. So, in terms of, I guess, the design philosophy behind the library, a lot of similar toolkits have what you could call a pluggable architecture. So natural language processing libraries like this kind of cut the problem of processing text down into lots of individual problems that all have an individual model behind them. So for instance, you typically start by taking the text and processing it into tokens. So you say, all right, instead of just a string, you've got some objects or some sequence of things, and then you're going to attach annotations through them. Oh, yeah, thanks. I wasn't paying attention. So, you know, you take your tokens and then you're going to predict part-of-speech tags for them, or a syntactic dependency parse for them, or try to recognize named entities or something like this. And for each one of these individual solutions, there's lots of different models that you could use. There's lots of different algorithms that you could use for part-of-speech tagging, and lots of different algorithms that you can use for parsing. So the typical way that people design these libraries is to say, all right, the library author stands back. We just provide this architecture. For each of these slots, you can slot in whatever model you want, and then that's it. And I think that this is really bad. So the reason why I think that this is, you know, a real disservice to consumers of the library and really not the right way to set up these tools is that if you set this up on the assumption that, okay, here's a slot for a part-of-speech tagger, use whatever you want. Here's a slot for a parser, which consumes the part-of-speech tags, use whatever you want. You're really telling people that the choices of these things are independent, and they never are. However, you have defined the later model that consumes the previous input, it has all sorts of dependencies in it. So in particular, if you're distributing a trained model, then if you use that pre-trained model with input that is not exactly the same as it was during training, your accuracy will be really bad. So if you change the tokenization from something different from what was expected during training, well, your model's weights are now no longer useful. And even if you retrain the model, there are all sorts of kind of subtle selections that go on when you're designing these things. So in practice, I think actually it's very difficult to kind of hot swap these components. And so that's why I've tried, in spaCy, there's much less emphasis on this. Instead, it's, all right, here's one pipeline that does the thing well, and then if we can improve on that as algorithms improve, then we'll swap those out and give you a better way forward, instead of this idea of having 5 different part-of-speech taggers. The other advantage of this is that there's nowhere in our API where we tell you to care about, you know, our average perceptron model. And so when we find a better experiment with the neural network, well, that swaps in and we don't have to break backwards compatibility. So this is kind of a key assumption behind the way that we've designed the library. It makes it quite different from other libraries like NLTK or GATE or Core NLP. And, you know, even though it's not what everybody else does, and in some ways people say, well, it's like super opinionated, I'm quite confident that this actually makes a much better user experience. Okay, so to talk through some of the specifics about how the library works and how it's designed. So the first part of the text processing pipeline is you take this string and you want to split it into words. And this is quite fundamental because when you're taking these words, you're going to be predicting annotations over them, etc. Now, there's a common problem in the way that a lot of this software works. Typically, if you have some function tokenize, it's essentially doing a more complicated string.split. So you get back this kind of list of the tokens where each token is an individual string. But then if you want to relate those tokens back into the original string, say for instance you want to calculate, you want to display markup, like you want to add a hyperlink around every named entity or something, then relating the annotations that you're producing back into the original document becomes super difficult. And so we've kind of lost information here, and we then have to do this annoying alignment procedure, and things get like tricky. Often even if these tokens are changed in arbitrary ways, then there's now no longer any simple alignment here. So one solution that people do is to say, all right, the tokens that you get back will be these offsets into the original string. So you get this kind of standoff annotation. So it's a very kind of XML-inspired sort of solution. So this is one common way that people try to solve this problem and make this less bad. Now, the problem here is that this becomes very bureaucratic. So in order to compare any of these tokens and just ask, okay, is token 0 equal to token 1? You now have to do all of these string slicing operations, and things become very expensive, and there's just all of this indirectness, right? So sure, you haven't copied any data, but on the other hand, the actual processing that you get back is like not very good. So this turns out to be something that works in theory. And as I say, it's an answer only a standards body could love, or maybe the European Commission or something. But this isn't tellingly, for academics who are doing these things and kind of producing these models, they never use standard annotation. It's too annoying. It just does not work well. But I wanted both, right? Like I really wanted to have the non-destructive tokenization because I think it's super useful for a lot of applications, but I also didn't want to do it this way. So here's the way that the solution that is in spaCy works. This is a little bit hard to read, but basically we want to keep this property of not copying data. So we don't want the tokens to be kind of a copy of the string. But we also don't want to just track these standoff pieces. So what we do instead is each token is indeed a piece of the string, but we make sure that we remember the place that it started in the original string, and then we also remember whether it had a space at the end of it. And then for any white space that separates the tokens that isn't a single space, those just become new tokens. So if you have a new line character or something, that's a token. And this means that by tracking this extra bit here for whether this token owns a space, we don't lose any of the information that's in the original string, and we're able to keep this attribute. The other thing that we do is kind of have this central repository of the lexical types. And this lets us cache like all sorts of attributes of these things. And this is nice because the number of lexical types will grow exponentially slower than the number of tokens that you see. Like if you process, 1 million words of text, the number of new words that you see in that million will be much, much less than when you see in the next million and the next million after that, right? You'll keep seeing new words, but the number will keep dropping as you keep processing more text. Okay, so I think I'll skip this for now unless we get into a lot of detail about it. Basically, actually there is a bit that I'll show. All right, so to make this a little bit more concrete and talk through the dependency parsing and basically explain how this part of the process works. So a key part of the analysis that's done by spaCy is trying to predict this, the syntactic structure of words, of the sentence. So if we have the sentence with oh, that's right down the bottom, isn't it? Is that actually readable? Because it looks probably not. Is it? Yep. Well, yeah, but wait. Okay, is that a bit better? Yep, okay, cool. All right, so yeah, imagine you're kind of processing this text and you want to extract information from it. I picked this up off a random Wikipedia article. So we see, all right, Irishman Stephen Roche, Vicente's teammate, took the overall lead for his team, and his team won stage 3 in the trial. So this is about some bicycle race or something. And there's all sorts of information in this sentence that you might want to be extracting out and filling into a knowledge base or filling into your application in some way. Like, so, for instance, there's the information that this person is Irish. So if you're reading the web and you're kind of getting this database of facts, the relationships between these two words and this word, that's going to give you that sort of information. Or, for instance, it'll give you, there's other information, like the fact that this guy is this guy's teammate. Or that, together they took the lead. So these, in order to get these this sort of information, one of the steps that we do is to get this kind of tree structure of these relationships. And the way that we do that is to iterate over the sentence, and at each point we're going to predict one of these actions that this little state machine is going to make. So these two words are currently on a stack, and this is a buffer that's looking forward, and we have here the word at the front of the buffer. So with just a few actions, we're able to make arcs between this word and words on the stack, or advance the stack forward. So So you see how this, by doing this, it kind of progressively builds these relations. And at the kind of beating heart of this is this big machine learning model that has lots and lots of sparse features, because the indicators are about individual words and attributes attached to them, and there's lots of classes. So the total number of predictors in this model is 9 million, because there's you have to have lots of features that say, like, is the next word took? Is the next word took and its part of speech tag is verb? And all of these things are, imagine like a spreadsheet with like 9 million binary columns. So in order to actually make this run fast, it's kind of backed by a hash table that just does lots of these lookups, and this also runs in essentially in C. All right, so moving forward. All right, so the way that this is all kind of implemented is there's underneath it all, there's these C-level structs that hold all of the data, and the Python layer just kind of sits on top of it and proxies calls to and from it. So if we, so I'll show you what that looks like in brief, which this also is way too small. Okay, so how many of you have used Cython at all? All right, so Cython's a Python-like language that essentially transpiles into C or C++ and makes calls into the Python C API. So essentially at the end of this, you get a C extension that you can import into Python the same way that you would import a C extension that you had written in C or C++. But the good thing is you get to write in this language that lets you mix high-level code that's essentially just looks like Python, and also low-level code that's type declared and is managed. So the way that often the way that people use this tool is to kind of write it in Python, and then you you compile that bit and you see, all right, this is now doing basically the same thing, but instead of doing it in Python and being byte interpreted, it's just making these calls into the C API. And then you can make it progressively faster by adding some type declarations. Now, this isn't the way that spaCy was written. Instead, this was really written from the ground up, thinking carefully about data structures and memory management. And in some ways this is harder, but in other ways it's actually a lot easier. So the part that's easier is, instead of trying to guess what the Python interpreter does and how it's going to manage memory and etc., you just do more reasoning up front. So you define your structs and basically set out to work. So, but in terms of how the actual Python API works then, you've got this, each of these token objects, well, this is just going to hold a pointer into the doc, into the, hang on, let me actually show you the declaration, like what this actually looks like. Okay. So underneath it all, the token just maintains a pointer into the this struct, and that struct there holds all of the information. So the idea here is that the Python layer shouldn't own any information itself, because any information that the Python layer owns is going to be duplicated information that you have to kind of then keep in sync with the C level. And duplicating information and keeping it in sync is bad. So instead we just have the Python layer proxy information to the C part. So for instance, if we want to ask what this attribute, its frequency rank, well, we just this is just a property, and it's just returning some attribute that it fishes off its struct, and etc. for basically everything else here. And this is the way that the Python level of spaCy works basically across the board. All of the kind of underlying things happen at the Cython level, and then the Python layer is just essentially this wrapper on top. In much the same way that it would be if you wrote it in the underlying level in C or C++, but by writing it in Cython, you get the availability of Python constructs, and you also get a more unified code base. You don't have this like sharp separation between a C++ layer and the Python API on top of it. Okay. Now, all right. So I'll go through. Right. Okay, so to tell you a little bit about what I consider the design philosophy of coming up with the API for Python and how to basically some of the considerations through it. So I guess the main thing that I was thinking about through this is trying to minimize the amount of stuff that people have to remember. So fewer names and fewer arguments and fewer named arguments to things. So I've ended up using a lot of the built-in operators, maybe a bit more than most libraries. So instead of a token doc.get I or something, it just uses get item. And similarly, instead of a function for process, I just used a built-in call function. And I think this actually ends up, in some ways it's a little bit less explicit, but it does end up being quite nice. And we're making every effort to make sure that processing different languages uses kind of a unified API. So in order to get the German model, you should just be able to change DE for EN here, and it should be give you this callable thing, which gives you back this document object to manage the annotations. Similarly, in order to do the multi-threading, we have this method .pipe, and this consumes an iterator of texts, and what you get back from it is an iterator over documents. And internally, this does all of the batching and threading and etc. that is necessary. So the idea here is that the user of the function shouldn't have to batch up the documents themselves. Internally, there is a buffer, but we can just draw in off this input stream, accumulate a buffer ourselves, do the work on it, and then yield it back out one by one. And the same thing can happen for every one of the process modules that is inside the pipeline. So, Python iterators are pretty cool. You can compose them this way very easily, so long as you don't break the contract and none of the individual models demand the batching be done for them. So long as they all operate as iterator in and iterator out, you can compose them all very neatly. Similarly, the get item is used to fetch tokens, and there's an iterator for the sentences at doc.sense. Then there's a few other iterators that for kind of contiguous spans of text. So integer IDs are all one of the things that's often difficult in natural language processing is that you typically don't really want to compute with strings. If you want to be using NumPy or Pandas or any of these other things, using text data is really a pain. So having integer IDs for every string is actually very useful. spaCy takes care of all of this for you. It assumes that basically you prefer to have integer IDs because most of the time what you want to do is kind of check identity. And there's other integer IDs for kind of some common views of the text, like the lowered attribute on tokens or this sort of thing. But other times you do need to get the original string back, and so every the kind of base name of these things is spelled without an underscore, and then the underscore is appended afterwards. Now, this name was naming things is very difficult, and this one, I ended up using this for like the basically unprocessed one, so it's like the original orthographic form. I'm not really thrilled at that name, but now I feel like I'm kind of stuck with it, and there's like various things of this where I probably changed some of these names like 5 or 6 times in development before release, and they still end up bad. It's one of these things where the more often you've had to change something, the more likely it is that it's the problem's kind of fundamental and you won't be happy with the answer at the end of it. Okay, so moving through, there's also support for word vectors on any one of these things. So, you know, for an individual token, you can ask what its word vector is, which allows you to get a kind of fuzzier representation of its meaning, and you can compare these things with like this similarity method. The similarity method can also be attached to the documents and arbitrary spans of text, and at the moment it just averages these vector representations to give you a kind of averaged view of the meaning of these things. But in future I want to have a more sophisticated way of getting you know, a vector for a document or a vector for a sentence or something, because people keep coming up with better algorithms for these things. Okay, so kind of moving through things. I'll go back through here. Yeah. All right. So I think I'll actually just wrap it up early. Yeah. Okay. So that was a pretty lightning tour through a lot of issues in this, and I feel like I didn't really put things together well as I was going through this. I was like, this is, you know, a bit of a grab bag, but I hope that questions can fill the gap with these things. I often like to take questions through it anyway. So.
Thank you very much. I'm sure there's going to be lots of questions. I can see, yes, already one question here.
Do you support just English? Thank you for the talk. Do you support just English or other languages too? Or do you plan to support them if you don't?
So at the moment there's support for English and German. We're going to have support for, you know, basic bag of word models in you know, a wide variety of languages very soon, but for the deeper support, which involves this, the syntactic parsing and etc., these things kind of need to be rolled out one by one. So we're working on Spanish and Chinese at the moment, but you know, these things take time. So at the moment, the idea is for deeper support for most languages, these will be kind of sold as expansion packs, and but there'll be free support for bag of words models for these things.
More questions?
Okay, so one question comes to the internals. So how do you attack pieces of speech?
Right. So it's a supervised learning model. So there's data sets of a couple of million words of English and, you know, about 1 million words of German that have been you know, kind of laboriously manually annotated for the part of speech tagging. Then given the training data, the actual statistical models that's used for this is super simple. We actually use an average perceptron model at the moment, which is a type of linear model. Essentially, at each word, you have statistical predictors for like the next word, the previously assigned part of speech tag. You make a prediction based on that. If you were wrong during training, you update the weights towards the correct one. If you were right, you leave it alone, move to the next word, make another prediction. So essentially it's just this process of, you can imagine it as counting up, oh, well, when I saw the last time that was a noun and I got it wrong, so I'm more likely to predict it a noun this time. And over a number of passes over the training data, this works out.
Hi, excuse me. You mentioned support for word embeddings and future support for sort of document level embeddings. What are you thinking is the state of the art on that at the moment, and what would you be looking to support?
So the algorithm I have my eye on at the moment for sentence level representations at least, and probably something like this for larger spans, is an algorithm by Bowman et al. That was published from Stanford. I think it was this year, but maybe late last year. So this is an algorithm that kind of does it's a lot like the transition-based parsing. It maintains this vector representation and has this, it manipulates that and ends up building a sentence representation. This was trained for paraphrase detection, and it's gets good performance, and the model convinces me. Like, it seems like it's the right kind of way to do this sort of thing.
Hi. Do you see any kind of functionality that relates to Spark or Dask or something with it?
So that's a good question.
Do you think it's a good idea, actually?
Right. We've had some problems with this in the past. To be totally honest, I haven't really used Spark much myself, and some aspects of the design of the library make this a little bit difficult. The models don't tend to be picklable. And actually, I'm a little bit worried about making them smoothly pickle, because then this encourages a workflow where people will map over individual texts. And if you do that, and you do this in a naive way, then the model will be reloaded on each text, which will give you a really bad experience. When I've processed large data sets in the past, like for instance parsing all of the Reddit comments for our SensiTiveX demo, I've basically just used one large machine with about 90 cores. The library multi-threads smoothly, and I just used something like joblib, or Dask would probably work fine as well, to just handle the multi-processing around it. So each process loads up a big batch of comments, like a month of comments in the Reddit data, and then within each batch use multi-threading to work the machine a little bit harder. If you're going to use this over a fully distributed thing over lots of different machines, then probably you need something a little bit more complicated, but I would probably use Spark to distribute the work at kind of the comment level, and make sure that it wasn't trying to load the model on each text, because that will be about 5,000 times slower than it should be. So.
Hi, I was wondering if you support informal text and how easy it is to customize for particular scenarios, say for specific entities that are not the standard ones, or.
Mm-hmm.
Yeah.
We have taken steps to try to get the statistical models to perform better on informal text. It is trained on a variety of text types, including some text from the web, and we have some functionality in there that processes the whole document at once. It doesn't assume that it splits neatly on punctuation or something, and we also have some data augmentation to, move in and have texts which are all lowercase or which have punctuation stripped and things. That said, depending on the actual conventions of the text that you're processing, some informal text is always going to be hard. And Twitter in particular has its own conventions and is often actually semi-structured, and the statistical models often don't work well in it. So there is kind of adaptation that has to be done for different text types. In order to in order to kind of add entity classes and stuff, yes, you can add the entity classes, but the way that it's set up at the moment, if you don't retrain the model with all of the entity classes, the statistical entity recognizer might not work that well. But there is good functionality in there to have pattern matching, and we have some tools and technologies that we're developing to help you build up lexicons, and so that you can kind of like click through and say, yes, that's an instance of the thing I want, that's not, and it kind of starts suggesting you things which are similar in meaning. So, we have plans for this, but at the moment it's still a little bit difficult.
Hi. So you said earlier that you can use multiprocessing or joblib at some kind of batch level, and inside a batch use multithreading using OpenMP. Doesn't it crash because the OpenMP runtime is not robust with respect to the fork system of multiprocessing? You don't run into that bug?
Well, no, I haven't actually hit that.
That's weird. We have it whenever we try to do that in scikit-learn, so we stopped using OpenMP because of this for now. But all right.
Yeah, okay.
We can take it later.
So, look, I didn't do anything fancy. There's just this Cython p range loop, and you know, it could be that JobLib does something more, like even more basic than fork, but yeah, I haven't hit that problem though.
Hey, I like the idea that you decided for the algorithms to both improve user experience and also quality of the pipeline. I wonder if you look downstream at the NLP pipeline, if you still can efficiently decide what the best model is, if you look at tasks like topic detection.
So if I'm understanding the question correctly, it's something like, all right, it's all well and good to have these evaluations that say, all right, we'll just have this one answer to this. But if you have downstream evaluations, maybe you find out that, oh, well, look, those 5 different models in there were all important because people did need them for different things. So no, I haven't run those tests, but I'm also not aware of any results in the literature that really point to that. What I've basically seen is that parsers, like algorithms which are just better at identity recognition, tend to just be better across the board. And actually, you know, you can develop an algorithm on one data set, and then, you know, you apply it across languages, and if it's got a robust improvement, then it's just better. And I do think that a lot of the times these things, you're looking at kind of what the manual annotation is, and you're looking at what the statistical model produces, and there's still a lot of basically inexplicable errors. And it's reducing these errors which are just clearly wrong, which, you know, are going to be bad for every use case, I think is what the real game is at. And so if you're getting like a 1%, 2% improvement in these things, I think it's just better. And I don't really... there wouldn't be an application where I would assume that I should use the worst algorithm because it might be especially good on this problem. I think the baseline assumption is that the more accurate model is just better.
Do we have more questions?
Thank you for the talk in the library. So you mentioned that there's a word vectors functionality in there. How did you decide which word vector model to use? Like, it's an unsupervised method. Like, is it some task that it works well on? How did you train it?
Well, so I actually decided and then afterwards redecided. So the first decision was pretty arbitrary. This paper came out and I was like, oh yeah, that looks pretty good. And I was convinced by looking at the results, and it made sense to me. So the initial release for spaCy has these word vectors from a paper 2 years ago by Yoav Goldberg and his student Omer Levy. Since then, I've regretted the choice, and now I suggest people just use the standard glove vectors that Stanford produced, because that data was trained on much more text, and it's what everybody's been using. So in the absence of any good evaluation, I suggest just using the standard things that other people want to use anyway.
Do we have any more questions? You're next.
Hey, you didn't say anything about the training pipeline that exists in spaCy. Is there any, and is it okay to use?
So yes, the training functionality is all there. We haven't held back any of the training code. That said, the training data is not there because we're not at liberty to release the training data, which we sub-licensed from the LDC. And in order to gain access to that, you have to be an LDC member if you're a company. If you're a student, then you're welcome to, or an academic, then it's easy to get these things and train the thing. But we haven't emphasized the training functionality because we think that on average, it's actually reasonably difficult to get these things all set up and running well. And we've found that mostly people want to use the pre-trained models. So there is some missing documentation about how the training stuff works. And to be honest, if you train it on different data, there tends to be basically little fiddles and different things that you have to do to make it perform well. Maybe you have to change some of the features or these sorts of things. So essentially training is fiddly, and we find that people on average lack the data, and so we haven't emphasized that part of the functionality. The part that we've emphasized is using it to process text.
Well, thank you. Let's give another round of applause to Matthew Honnibal.